Hi! Crash Course Physics posted their second episode yesterday. Or was it Crash Course Mathematics? Derivatives it is indeed. Let's shed some light on the physical meaning, which has been left out quite a bit in their video. After that, I will show you the geometric pictures behind the laws of derivatives that have been presented. There's a lot to cover today. I don't believe in stockpiling math ahead of applications, so I will reference examples from physics as much as possible. Derivatives are rates of change. That is their prime meaning, especially in physics. When you fill a sink with water, for example, the volume changes as a function of time. You might open the tap further, or shut it completely, or release the plug. The basic question is, how much does the volume change from one instant to another, that is, over a short interval of time dt? If dt is indeed short enough, we may consider the function v of t as essentially linear, represented by a line tangent to the graph. This line has some slope s. Then the new volume is the old volume v of t plus s times dt. The slope is thus the rate of change of the volume, or in fancy words, its derivative. So the derivative is the rate with which water flows into or out of the sink. As this rate may itself change over time, it is a function which we write v prime of t. While the unit of volume is liters, the unit of its derivative, the flow rate of water, is liters per second. Let's look at a few other quantities and their rates of change. In a thundercloud, a positive electric charge is accumulated. The symbol for charge is Q, and it is measured in coulombs. When the cloud discharges, we see its flow as a lightning bolt. The flow rate is electric current, the derivative of electric charge. Its unit is coulombs per second, or, as you may have learned them, under the name amperes. The power of a microwave, given in watts, is nothing else than the rate with which it can transfer heat energy to your food. Energy is measured in joules, watts are therefore joules per second. Again, we see a quantity and its derivative. Next, the power rule. It appeared somewhat out of the blue, even though there is a strong link to the kinematics from last episode. Imagine your position as a function of time being 5 times x squared. Let's watch our units. The prefect of 5 is in meters per second squared. Applying the power rule to first find the velocity, and then again to find the acceleration, this turns out to be a constant 10 meters per second squared. This is precisely the kind of uniformly accelerated motion from the second kinematic equation. The factor of 5 is nothing other than half the acceleration. Now a more advanced case. Imagine your position changes over time as t to the third. Taking the derivative once, then twice, yields an acceleration of 30 times t. So the acceleration is not constant here, but itself increasing linearly. The prefactor of 30 is in meters per second cubed and called jerk. No, not that kind of jerk, but the kind of jerk you experience when you mix up the gas and brake pedals in your car. But what magic lies behind the power rule? How does it work and why? To answer this, let's look at the derivative of t squared, or the area of a square with the side length t. If we increase the side length by a small amount called h, the main contribution to the area comes from these two thin rectangles on the sides. Each rectangle is t times h, so the increased area is approximately t squared plus 2th. We recognize the factor in front of the small change h as precisely the derivative of t squared. The cubic function can be represented as the area of a rectangle with sides t and t squared. As we increase t by a small amount h, how does the area change? Well, the answer lies again in these thin rectangles. T squared changes by 2th, so the rectangle's area are 2t squared h and t squared h. The total change is thus 3t squared times h. The derivative of t cubed is thus 3t squared. Maybe you can already guess how this continues. For t to the 4, draw a rectangle with sides t and t cubed. Increase both sides by h and 3t squared h respectively, then the thin rectangles are t cubed h and 3 times that, yielding a derivative of 4t cubed, and so on. What about the derivatives of the sine and cosine functions? These lie at the heart of any kind of circular motion, of which there are a lot in physics. Let's take for example the Earth that is revolving around the Sun at the distance of 1 astronomical unit. Introducing axes, the coordinates of the Earth will depend on the angle traveled, theta. Actually, theta is here measured in radians, so it is simply the arc length of the unit circle. Then the x-coordinate is cosine theta, and the y-coordinate is sine theta. If the Earth moves by a small angle d theta, we may ask by how much its position changes in x and y. Let's zoom in. Look! There's a right angle, and there's theta again. The hypotenuse of the triangle being d theta, we can calculate its legs using simple trigonometry. We can thus write the following approximations. The sine of the increased angle is the old sine plus cosine theta d theta, and the new and improved cosine is the old cosine minus sine theta times d theta. The sine and cosine are thus each other's derivatives, up to a sine flip. Finally, let's take a look at exponential functions, which describe, you guessed it, exponential growth. This occurs whenever the rate of change is proportional to the quantity already present. More people make more babies. More neutrons produce more nuclear reactions. Such functions are all basically of the form y equals a to the x. Among them, there's a special one. If a is that special number e, the derivative at 0 is simply 1. We've already said that the derivative as a function is simply proportional to e to the x, but why is it precisely e to the x itself? Well, with a given tangent of slope 1, we find that for small numbers h, e to the h is well approximated by 1 plus h. But then, when we play the same game as before, e to the x plus h becomes e to the x plus e to the x times h. So the derivative of e to the x is e to the x itself. In other words, the exponential function e to the x is the one function whose rate of change is always precisely 100%. So I hope these explanations have been somewhat helpful to digest this half year's worth of mathematics, and I hope you'll join me next week for integrals.